In this tutorial, we will explore EHR data using R and RStudio, working with a synthetic dataset that simulates GIC patient data. We'll understand the PIC-SURE EHR data structure and perform basic data analyses. This tutorial is designed for those with basic R skills. Topics covered include setting up the R environment, loading data, assessing key variables, and running basic analyses. Setting up the environment. First, we'll install some essential R packages. These packages provide functions to help us manage, manipulate, and analyze data effectively. Specifically, Tidyverse includes a collection of useful tools for data analysis. Lubridate helps us work with date and time data, and the HTTR package will allow us to fetch the synthetic dataset from the GitHub repository. You can load other packages using the install.packages function. Once the packages are installed, we will load them using the library function. Loading the dataset. Since our dataset is hosted on GitHub, we first define a variable containing the dataset's URL and use the get function to download the file. If your data is stored in a private study folder on Service Workbench, you can directly specify the file path to your file instead of downloading it. Next, we will load our data into an R data frame using the read CSV function. Examining dataset structure. The dataset's timestamps are stored in Unix format. Before analyzing the data, we will first convert these timestamps into a standard date-time format. To get an initial understanding of the dataset, we will use the head function, which displays the first few rows and helps us examine the structure. The dataset will consist of 5 key columns. First, patient num, a unique identifier assigned to each patient. 2, a concept path, which is a hierarchical structure that narrows down to a specific clinical variable. 3, tval-char, which stores text-based values. 4, nval-num, which stores numerical values. And 5, the timestamp, which represents the date and time of the recorded observation. For demographic data, this timestamp reflects the date of the last data refresh. To better understand the dataset, we will analyze the highest level of each concept path, or variable type, to identify the different types of data. Each distinct category within the concept path will be referred to as a variable type. In this section, we will classify each variable type and count the number of observations associated with each. The dataset contains 5 primary variables, including demographics, diagnosis, lab test results, medications, and procedures. In the next sections, we will explore each of these variable types in greater detail. Analyzing patient demographics. In this section, we will explore, organize, and visualize demographic data, including age, sex, and race. To begin, we will create a new data frame titled demo_df that extracts only demographic-related observations from the original dataset. We identify sex-related observations by searching for relevant values in the concept path column using the grepl function. Since we are only interested in patient ID and sex, we select corresponding columns and rename the tval-char to sex for clarity. Next, we generate a summary table showing the distribution of sex in the dataset, grouping by sex and calculating the percentage of each category. Similarly, we extract age-related observations, selecting and renaming the nval-num column as age is recorded as a numerical value. To visualize age distribution, we will create a histogram defining the x-axis as the age variable. And using the labs function, we can label the axis and provide a plot title. We also categorize patients into 3 distinct age groups and summarize the number of patients in each. This is done by creating a new data frame that includes an additional age group column, followed by calculating patient counts per group. Following the same approach, we isolate the patient race data by filtering the concept path for race. The relevant values found in T-val-char column are stored in a new column called race. A summary table is then created by grouping by race, calculating the percentage of each category, and rounding to 2 decimal places for readability, and arranging the table in descending order. We visualize these results using a bar plot. The original dataset structure makes it challenging to view multiple demographic attributes for a single patient at once. To address this, we merge the age, sex, and race data frames into a unified table, organizing all demographic details by patient ID for a more comprehensive view. Analyzing diagnostic data. In this section, we will analyze diagnosis codes related to our area of interest. For this example, we will focus on epilepsy, which is categorized under the ICD code G40. If you are investigating a different disease, you can modify the ICD-10 code accordingly. To begin, we will create a new data frame containing diagnosis-related information by filtering for ACT diagnosis as the variable type using the grep-L function. Then we create a new variable called ICD code of interest and set it to G40. You can replace G40 with any ICD code of your choice. Next, we will create a new variable called epilepsy_ICD-10 and filter the diagnosis data frame to include data entries with G40. For clarity and ease of interpretation, we have renamed the T-val-char column to ICD-10 code. Next, we will examine the demographic characteristics of epilepsy patients by merging the list of epilepsy patient IDs with the demographic data frame we created earlier. To further our analysis, we will investigate how many epilepsy patients also have a migraine diagnosis. We do this by first creating a list of patients with migraines, following the same steps used for epilepsy. First, define the ICD code of interest as G43. Next, filter the diagnosis data frame for migraine-related diagnoses. Then merge the migraine patient list with the epilepsy patient list using the inner join function. This ensures that only patients diagnosed with both conditions are retained. Next, we will merge the data sets to include a column that indicates whether a patient has a migraine diagnosis. We merge the combined epilepsy migraine patient list with the epilepsy demographic data frame. A new column is also created to flag a migraine presence as a binary value. 1 equals has migraine, 0 equals does not have migraine. Then we calculate the percentage of patients that have migraines in our epilepsy cohort. Analyzing medication data. Next, we explore the medications data by filtering entries where the concept path variable contains the term ACT medications. To get an initial overview, we use the head command to display the first 6 medications. In this example, we aim to determine whether or not a patient has been administered carbamazepine or pregabalin. We will search the dataset for these medications and identify the patients associated with these observations. This table indicates whether a patient diagnosed with epilepsy was ever administered carbamazepine or pregabalin. Analyzing lab test results. After creating a new data frame that includes only the lab result data, we will then generate a list of available lab tests, similar to how we did for medications. Please note that the lab result entries can vary significantly per patient, with multiple results recorded even within a single day. In the statistical summary and visualization, each lab result is treated as an individual data point, without applying weighted averages or other statistical adjustments. For this example, we will focus on AST, aspartate aminotransferase, and ALT, alanine aminotransferase, lab results from 2023. If needed, you can replace ALT or AST with any other lab test name, as long as it appears in the dataset. To include multiple tests, simply add a vertical bar between names, which functions as an OR operator in the logical expressions. Here we create a new data frame that includes only AST and ALT results from 2023. To enhance readability, we will replace the concept path column with the lab test name for easier visualization. Then we will create a summary statistics table for each lab test in the filtered dataset. Here we use a box plot to visualize the distribution of ALT and AST values in 2023. Lastly, we will analyze the AST and ALT trends for a single patient during the year 2023. This can be useful for tracking liver function trends following a specific event, such as monitoring an epilepsy patient's liver function after starting carbamazepine treatment. To analyze a different patient, simply modify the patient of interest variable. In our ggplot visualization, we use both the geom line and the geom point function. The geom line connects the data points to highlight trends over time. The geom point adds individual dots for each measurement, ensuring that both the overall trend and specific values are clearly visible. Analyzing procedure data. Similar to our approach with the other variable types, we will generate a list of unique procedures. However, this time we will combine filtering and listing unique values into a single step for efficiency. In this example, we will focus on appendectomies. We will filter the procedural data to identify patients who have undergone an appendectomy since the beginning of 2020. Thank you for following along. In this tutorial, we covered how to set up the RStudio environment, how to load patient data, assess key variables, and perform basic analyses. If you need further assistance, please contact the GIC service desk. We're here to help.